All right, so today we're looking at lesson 2.2. We're going to talk about the distributive property. We're going to talk about factoring, so kind of the reverse direction of using the distributive property. And then we're going to talk about combining like terms, and that's going to be our main focus today. And that's something we looked at in middle school in Math 7 and Math 8, but we're going to dive a little bit deeper into it today. So the big idea is to apply the distributive property. You can add or subtract like terms. And so we need to make sure we understand what these all mean. So like terms are terms, and you probably already have this written down, but just in case you might need to change some things to make it make a little more sense to you. So terms that contain the same variables. So you're talking about your x's and your y's, but they also need to be raised to the same powers. So if it's an x and an x squared, those would be unlike terms. So they have to have the same power. So x and 2x, those are like terms. X squared and 5x squared, those are like terms. But 6x and 3x squared, those are not like terms. They have the same variable, but they have different exponents on those. Okay, so they got to have the same exact one. Now, the coefficient is the number that precedes or is being multiplied by this variable. So this is a number that is a factor in a term. So sometimes in a term, you've got a product like 2x, right? 2x is a product. It's 2 times x. And a factor means you separate the two things that are being multiplied. So the 2 and the x are the two factors of 2x. So x is the variable and 2 is the coefficient. It's the number that's one of the factors. Now factoring undoes expansion by using parentheses to factor out a common term. It's basically backwards of the distributed. Okay, so what does that look like? So for instance, if I have 2x plus 6, and I want to go back into something that has parentheses, I can take the 2 or factor it out and think about, okay, there's two terms in here. 2 times something got me 2x. So that's x, because 2 times x is 2x. And then this would be 3, because 2 times 3 gave me 6. So we all can distribute 2 times x, 2 times 3, and get this, but can we go backwards? So that's factoring. So first of all, we need to understand what like terms are. So real quick, example number 1. Determine whether the term 8m squared is like terms with any of these. So first, this one, they both have the same variable, but that variable does not have the same exponent. So this is no. I could not combine these two together. There's a big difference between 8m squared and 8m. Now this is 8n squared. Looks close, kind of looks like 8m squared, but it does have a different variable. So again, this is no. This one has a different coefficient, but that doesn't matter. The number in the front, the coefficient, does not have to be the same. The variable needs to be the same, and the power of that variable needs to be the same. So these are both m squared. So this is a yes. So we could combine these like terms. If we did put these together, if you combined 8m squared and negative 4m squared, your final answer is still going to have the m squared, and you're just adding the coefficients. So 8 plus negative 4 is just 4. So like terms can be combined. They have to have the same variable and exponent. So when we look at this one, I see m squared, and if it was just 9m squared, then I would say yes, I can combine those. But as soon as I add this n, I have another variable that's part of this product, then this is a no. It's different, I can't combine it. And what about just m squared? Well, does the variable match? Yes. Does the power match? Yes. So I can combine this. If you remember, there's always a 1 in front of this. So if I was going to combine 8m squared and m squared, those are like terms. I can combine them. This is a 1 and an 8. So this would become a 9m squared. All right, so kind of using that same logic now in example 2, let's combine like terms here. So first of all, you want to figure out which ones are like terms. 8y to the third can combine with y to the third because it has the same variable with the same power. This 5y is different, not a like term, so I can't combine it with any of that stuff. So only these go together. It's an 8 and a 1. So this becomes a 9y to the third, and that plus 5y has to be left separate. That is not a like term because the power is different. So I need to leave them separated. So if I go to example 2, I've got an f squared and I've got an f squared. Now when I start combining these, I need to consider what's in front. If this says minus 10, that's like a negative 10. So I'm actually putting a 4 and a negative 10 together. I'm adding them. So you can think of this as 4 plus negative 10, which is negative 6. You can also think of it as 4 minus 10, which is negative 6, because adding minus 10 or negative 10 is the same as subtracting 10. So I'm going to get a negative 6f squared. Sometimes it's nice to just cross them out as you go so you know you're done with them. Now, when we put these in order, proper order, you're going to put any variables you have in alphabetical order. And if you have different terms that have the same variable but the powers are different, then anything with a power would come first, and the highest power would go before any other. So if there was an f to the third, it would go up front. So right now, f to the second is the highest power that we have. But now I also have these two right here that have just an f. Now those are like terms and they can't be combined with this. So they're going to come create their own term right here. Now, this is a 1f and a 120f, so that's 121f. So they're gone. Now, single numerical terms here, just numbers, they are like terms and can be put together. That's a positive 9 minus 30 or a positive 9 plus negative 30. Either way, that's going to get you a negative 21. So you could write plus negative 21, or you can just write minus 21. Either one is fine, but let's make it as simple as possible. If you get a negative, write minus. Okay, so we have now completed this problem. We've combined everything that is considered a like term. All right, going to the next page, example number 3. So we're going to write a simplified expression for the perimeter of the quadrilateral here. So perimeter is distance around the outside. So it's literally measuring every single side and adding up all of those lengths. So they've given us some expressions that represent the side lengths. We don't actually have a value. But if we did, we would add them all up. So what we're going to do is just write a long expression that shows that we're adding these all up. So perimeter equals this plus this plus this plus this in any order. We've talked about addition is commutative. That's the property that represents commutative addition. You can add them up in any order. Okay, so I'm just going to start with 5u minus t plus 4u plus 2t plus u plus 7t. Okay, so I've added up all four sides. So if I knew the values of u and t, I could plug them in, find out the side lengths, and I would add them all up to get the perimeter. Or I could just use this one long expression, plug in for t and u, and this will produce perimeter. Now, if I'm going to do all that, I might as well simplify this so it's not such a long process. I've got lots of terms here that are alike. Now, I need to be careful here. These plus signs kind of look like t's. So do make sure that your t's and your plus signs look pretty different. So as I kind of glance across this, I've got u's and t's, and that's it. Here's a u, t, u, and a t. So there's no just regular numbers, and there's no other variables to deal with. So if I simplify all of this, I'm only going to have two terms. I'm going to have my term with the u, and I'm going to have my term with the t. So let's start with the u's. I've got a 5u right here. I've got a 4u. Notice that I boxed in the plus sign, so I know it's a positive 4. I've also got this plus u right here. That's not a t, that's a plus. And if I quickly glance over this, a t, and a t. So the rest of my terms would not be considered alike with these. So combining all those, that's a 5, that's a 4, and that's a 1. So 5 plus 4 plus 1, that's a 10u. So if I combine all my t's, this is a negative 1, this is a positive 2, and this is a positive 7. Let's cross out those u's so we don't use them on accident. So if I just did the 7 and the 2, that's 9. And take away 1 because it's a negative, that's 8. So I have an 8t. Now technically I want to put these in alphabetical order, and t comes before u, so I'm going to put this t term up front. So that's a positive 8t. And since this 10 was positive, it's going to be plus. So this looks good right here. Now again, these plus signs and these t's start to look alike. So it might be better if you capitalize the t. It does not make a difference. And you could capitalize the u if you wanted to, but I think that's just fine. It doesn't look like a number to me. So either one of those are fine. You can capitalize if you need to, just so you don't kind of get mixed up between the plus and the t, because you can see how that could happen. All right, so that's kind of an applied version of combining like terms. Last thing we want to talk about today is factoring numbers out of an expression, and this is, again, kind of backwards from distributing. So example number 4 says we want to factor 8 out of this expression, 8x plus 8y. So if you notice, I have an 8 in both terms. So what I want to do is I want to factor that out. So I'm going to pull that number out, and I'm going to leave something inside parentheses. And you can kind of just think backwards. First of all, I have 2 terms here, so I'm going to end up with 2 terms in here. 8 times the first term has to give me 8x. 8 times the second term needs to give me 8y. Now, if I'm multiplying 8 times something and getting 8, that means the coefficient is just 1, because 8 times 8 would give me 64 over here. So don't automatically throw another 8 in here. So what would I multiply 8 by to get 8x? That's just x. 8 times x would produce 8x. What about 8y? What do I multiply 8 by to get 8y? That's just y, and it's a positive y. And this is my answer. So if you went backwards and distributed, you can always double check. 8 times x, 8x. 8 times y, 8y. So I kind of reversed the distributive property. Pretty simple if it's just numbers, but what if I'm factoring out a variable? So here's my expression, 2x squared plus 4x. I notice that both coefficients have factors of 2. Okay, I can multiply 2 times 1 to get this and 2 times 2 to get this. And I also notice that both of these terms have the same variable of x. Now, there are different terms because this one has the squared, so these could not be combined. They're not like terms, but they both have a factor of x. So I'm going to take the 2x out of it because that's what it's asking me to do. So 2x times something got me 2x squared. Well, that's just x, because if I multiply 2x times x, these x's basically combine to get 2x squared. Now, what about 4x? 2 times something got me 4x. I've already got the x here, so I don't want to put another x here, because if I multiplied this 2x times another x, then I'd end up with a squared or something like that. So since I didn't, I know this is just a number. All that happened was the 2 became a 4, which means I multiplied it by 2. Now, going back to factoring out 2x from 2x squared, sometimes that's confusing. Think about what 2x squared actually looks like. It's 2 times x times x. That's the x squared. X times x is x squared, repeated multiplication. And when you factor it out, you're kind of dividing by whatever it is you're taking out of it. So I'm trying to take a 2x out of 2x squared, and I'm trying to see what was I left with. So these 2's kind of cancel, the x cancels, and so what am I left with? The x. All right, let's jump down here. 3z squared, we want to take that out of this expression here. So I'm going to have 3z squared on the outside, and I need to figure out what's on the inside. Now let's try and figure out what am I going to take, or what's going to be left after I take 3z squared out of this. So I'm starting with 3 times m times z times z. That's what I started with. And I'm trying to take out 3 times z times z because it's z squared. There's 2 of them. So what cancels? 3's, the z, and the z. So what am I left with? M. So if this visual helps you, you can use that. Or you can just say, okay, I had 3z squared, and I multiplied it times something, and I got 3mz squared. So the 3 is still there, the z squared is still there. What's the only thing that added? The m. Now over here, I see that this is a minus. So I multiplied the 3, positive 3 times something and got a negative. So I know that this is a minus. And now I got to figure out 3 times something got me 6. Okay, so that's clearly 2. That z squared shows up in both spots. So I don't have another z here because then my exponent would be higher than 2 as a result. But all of a sudden I added this p, so that means there's a p in here. Okay, you could have also gone to 6 times p times z times z. And again, you're taking out 3 times z times z. We took out 3z squared. So your z's cancel. And the 6 and the 3 simplify to 2 over 1. And so you've got the 2p, and that's where this comes from right here. So you can always fall back on this if this is helpful for you for factoring.